Okay, so welcome back, everybody. This is our resumption of the daily lectures after we had the supplemental lectures fill in to basically cover a block of material from. We actually covered Markov chain stuff and some applications before we moved on, but yeah, you got to see now some data approximation, image processing, character recognition, some basic graph theory, very basic graph theory, some basic cryptography. Like you've seen a smattering of topics, some of which are going to be the subject of your next homework. Of course, your midterm. That I assigned yesterday is due tonight. But anyway, starting on kind of the next block of material, computer graphics. So specifically talking about 3D computer graphics here. So we won't talk about this necessarily from the point of view of making like a 2D game. So 3D graphics. Uh, and what is goal? Maybe maybe put this as our ultimate goal here for this block of material. So the goal is to how to work with points in 2D and 3D in such a way that the movements and projections can all be managed with matrix multiplication. This is Math 401, right? It's applications of linear algebra. So if we can make our computer graphics problem manageable purely through matrix multiplication, we're very happy. So the goal is to make, we'll say, manipulations or standard movements, depending on your geometry recollection. You might recognize these as isometries. Okay, Euclidean rigid motions, whatever you want to call them, to make standard movements, i.e., rotations and translations. Now, you you may notice, depending on how much you know about isometries, you might notice that, oh, well, reflections are included there too, right? Maybe even glide reflections are included there. Um, that's true from the point of view of isometry, but if we're talking about like managing this in terms of we'll say typical game movement, then dealing with rotations and translations is seems to be the more fundamental or basic thing. Now, before you immediately object and say, but isn't every transformation really a reflection or a combination of reflections, some number of reflections, one, two, or three reflections? The answer is yes, that's true. But we'll see that for practical purposes and for the things that we want to do, that doesn't necessarily help us that much, even though that is true. So rotations and translations to make standard movements, i.e., rotations and translations, as well as projections. So we want standard movements as well as projections. What is projection and why is this important? Well, if we're doing 3D graphics, your 3D graphics are going to be displayed on a computer screen in a two-dimensional fashion, right? You're looking at a flat screen. This is a two-dimensional representation of your 3D graphics, and so this is going to be turning 3D into 2D for your screen. Okay, I want both of these things, these standard movements and these projections, to be doable with matrix multiplication. That's what I want. Okay. Now, first step. We represent a point by a vector. Okay, that's nothing new here, right? In fact, maybe the first day of Calc 3 or first day when you were dealing with vectors, well, depending on the context in which you've dealt with, you were first dealing with vectors, maybe this wasn't the case, but it's probably been beaten into your head at this point that, points are vectors, vectors are points in a sense, right? This is how we deal with these things algebraically. Represent point as vector, so point in 2D you can think of as vector. Oh, not XYZ, just XY. Of course, point in 3D you can think of as a vector in 3D. Of course, there's a couple of things here, right? Maybe immediately what I'll say before I get into how we're going to deal with these things is my favorite example of various pitfalls that can happen when you are dealing with computer graphics like this. So here is an example. Strafe jumping in Quake. Now, in the original Quake, this worked a little bit differently. The way that strafe jumping was handled. So maybe I can clarify this if I really talk about the way that this works in like Quake 3. But the thing is that there arise problems when you are trying to do this, and of course it is relevant to note here that Quake's 1996, so this was actually one of the first. This is one of the first truly 3D games. It might not be exactly the first, but it's one of the first truly 3D games. What do I mean by truly 3D? So you had games like prior to Quake, you had Doom, you had Wolfenstein 3D, you had Build Engine games. And the way that those, I'm pointing out first-person shooters here just because it's an easy example, and they were some of the first. So those games, the way that they dealt with space is essentially everything was all of the models, all of the like enemy models, for instance, all of the models of everything in the game. If you ever played those games, will notice that all of them are actually 2D sprites, and based on the view angle that you're looking at the thing, the 2D sprite just rotates. So it's not truly a three-dimensional model sitting in three-dimensional space. It is a like two-dimensional sprite that rotates in this fashion. And even the way that the maps were constructed are not really true 3D, and I don't want to get too much into like what I would call true 3D here, but just suffice to say that Quake was one of the first truly 3D games handled in this way, and so they were solving some issues in computer graphics at the time that hadn't really been done before, and there were like some novel things slipped in to the code to address some of these things, but one of them was okay. So just like simply how movement or momentum is assigned, right? So here's player character, and we'll say I'm just looking from the top down. When you press, say, the arrow keys or WASD, right? Like, how does that tell the player character how to move? Well, what you might do is, your arrow keys, right, or WASD, regardless, I'm not going to write them as WASD, I'm just going to write them as arrows. So here's your keys. You can think of them as D-pad or four directional inputs here, right? So when I press the top arrow key, right? When I press this thing, how does my character move? My character I want my character to move forward ideally, but how do I do that? Well, I could say, all right, so I'm going to assign a unit vector pointing in that direction, right? If I just hit that key, right? So this would indicate my character moving straight forward. If I hit this right key, right, and I'm in a this is a strafe control FPS, not a turn controlled FPS. So in ancient times, when you hit the right key, your character would turn rather than strafe, right? But the way that this is going to work is that when I hit the right key, my character just moves right. Okay, strafes right. And again, the same thing is basically a unit vector is assigned to that direction, and then there's some specified units that are moved. And the way that this was handled, like how movement was handled, is when you started movement, you accelerated at some rate, but very quickly you essentially topped out at a max speed. Okay, we'll say 300 units per second, right? Depending on the Quake, it might be 320 units per second. It might be more than that, but it's whatever. In the in-game units, it's like, say, 300 units per second, we'll say. What is happening here? So basically, if I hit the right key, I strafe in this direction, and pretty quickly I accelerate to... This is how the game works. I'm not saying this is like, oh, logically, this is how it has to work. No, this is just the system that they devised. Very quickly, you accelerate to a top speed, and if you continue, say, holding the right key, you're just going to keep strafing in that direction at that max speed. You're never going to go faster. You're going to top out at this capped speed. Same thing is true if you hold the forward arrow. You're just going to go forward at that capped speed. Once you accelerate to that capped speed, that's it. Okay, now the question is, what happens when you hold a combination of the arrow keys? What happens when you hold a combination of the arrow keys? When you hold a combination of the arrow keys, instead of you getting this unit vector here or here, you get the sum of these two unit vectors. And now you're thinking to yourself, well, is the sum of two unit vectors necessarily a unit vector? You can think to yourself about whether or not that is the case. But I can tell you right now that what ended up happening here is that, well, this thing that resulted, this combo vector that I get by adding these two vectors, introduced what was a bug, what was not intended, which was all of this I just said had to do with on-the-ground movement. Okay, so this is if you remained on the ground, then essentially you were moving at this capped speed. Okay, what happens when you do this combo thing? If you hold two keys, you will run faster than the capped speed at first, but then you will slow to the capped speed. So this allows you to briefly go faster. Now, there's in older FPS games like Doom, there's strafe running. There were some strafe running exploits for this, or bugs in the same way, and it's basically that they forgot to renormalize these vectors, and they forgot that when you sum two unit vectors, you don't necessarily get a unit vector, and this extra length was essentially adding to the momentum or adding to the speed of the player. The way that this was handled in Quake was that if you remained on the ground, you would slow very quickly down to that capped speed. But what you could do is this slowing, you could call it friction if you like, didn't apply if you were in the air. And so in the middle of doing these, I'm not going to go through the inputs that you have to do, but basically through inputting, holding certain arrow key combinations, and turning your mouse as you bounce along, as long as you remain jumping constantly, you can maintain any gained momentum from this little trick, and you can go as fast as you want to, as fast as you can, essentially, as fast as you can control, uh, depending on the game. And the point is, you can go way faster than any other method of getting around. This led to strafe jumping. Now, what is this? This is something as simple as like the absolute basics of movement in your game, right? How the player character is translated. This very simple thing here and some other choices in how the game physics works led to like a very like a key defining feature of the game itself. It was originally a bug, was going to be patched out, and various threats were made, and it was not patched out because it was too much fun. So um, so what am I telling you? Am I telling you to that when you set about to do game programming, either graphics or otherwise, you should intentionally make your game buggy if it's fun? Uh, Maybe. I don't think I'm exactly telling you that, but I guess the point is that sometimes, what you intend to do in these with these things is not actually the optimal for fun. It's not necessarily the optimum for fun with regard to player experience. But anyway, the reason I wanted to include this is because thinking of how the movement vector is assigned and how the translation of the player character goes is like key to this, right? This is like the fundamental thing here, and there's actually several very thorough treatments of strafe jumping in Quake. Whether you're talking technically in Quake 1, it's bunny hopping is the thing that you're doing. There's all sorts of different things you can look into if you're interested in how this goes. Like I said, this is of interest to us in this section primarily because we are interested in how the graphics are going to be how we're going to implement graphics in the computer game in question, and very very subtle decisions on how these things are handled can lead to big impacts. But this is a fun example showing how even something as simple as like just direction assignment in the movement can lead to things like this. Anyway, so now for something completely different. What I want to do is so let's maybe think about so we'll start in 2D. But even before we get there, maybe first recall some facts about linear transformations. So what is a linear transformation? Linear transformation is a function or a map between vector spaces. So I'm going to use the words function and map interchangeably when I talk about these things. What is a linear transformation? So we say T is a linear transformation we'll use the notation T from V to W. V is called the domain. W is called the codomain. Okay. Which is not the same as the range. If you remember, the range is the image set of T. That's the range of T. That is different than the what we call codomain, which is all of W itself. We say that T is a linear transformation between vector spaces V and W if T, we'll say the first thing, T of CV is C T of V for all scalar C. Now I'm going to call this scalar a real number, but this definition works the same even if this is like a complex scalar instead. And for all vectors V in V. And similarly, The other thing for all vectors v and w in V, I know that this might be confusing. Maybe I should have used v1 and v2 here. This is the case. The thing, of course, to note here is that if I apply a linear transformation to a linear combination of vectors, what I get is a linear combination of vectors. So here is a linear combination, and here is another linear combination. So a quick and easy way of describing what a linear transformation does is it's a function between vector spaces that sends linear combinations to linear combinations. Okay, so it respects linear combinations, and linear combinations are the building block of vector spaces. So these are your fundamental building blocks of the vector space itself. So what it really means is a linear transformation is a transformation that respects the vector space structure. It preserves the vector space structure, okay, between T or V and W. Okay, now you might recall from Math 240 that there's a variety of things, of properties that a linear transformation can have. There's a lot of examples of linear transformations. You might notice that most of the examples that you dealt with in linear algebra were, in fact, given by matrices. So here's an example. You know, let Tx be, we'll say let X be the matrix, we'll say, or sorry, not the vector 3, 2, 1, and let Tx be defined to be Ax, where A is the matrix 1, 0, minus 1, 2, minus 1, 1. So in this way, T goes from where to where? Well, it takes in a vector in R3, right, and sends it to a vector where. So when A multiplies X, what do I get? I get a vector with 2 entries, right? Okay, and you can check T is linear. Okay, in fact, any transformation or any function between vector spaces defined by matrix multiplication is going to be linear because matrix multiplication itself is linear. It respects, algebraically, it respects those operations, right? So that's one thing you notice. Here's another quick example, just to remind you. But not every linear transformation between not every linear transformation is a matrix. Now, what do we mean by is? We mean it has some matrix that represents it in the sense that I can use this matrix A to attain what it is that T does on all points. We would call that the standard matrix for T, and we'll talk about that in a second. But not every matrix, or not every linear transformation is given by a matrix in this way. So quick examples, you might, if I wrote that on a board, right, and no context, I didn't say anything else, if I just wrote this on a board, and let's say I replaced T with D, and here, Of course, we can combine them like we did here. If I wrote those three properties, but really these isn't three properties, this is a combination of these two. If I wrote these two properties on a board with no context, said nothing else, and just said, well, what is D? Right? You probably not say a linear transformation. You probably say something else. Right? And if I replace D with I, you might say something else. Right? So what would you say? For instance, D, which is the derivative, or I, which is the integral. Either indefinite or definite, doesn't matter here. Here, I'll write it as definite integral regardless, I don't care. So here, what are these things? These are also linear transformations. But can fail to have a matrix that represents them. These are like your canonical example of a linear transformation that might not have a matrix representative or doesn't have a matrix representative. So notice I said might not because actually in the case that V and W are finite dimensional, they actually are going to have a matrix representative. But if V and W are infinite dimensional, they will not. So if V and W are infinite dimensional, they will not have a matrix representation. Now, depending on what your 240 instructor said about isomorphism of vector spaces, there's the other thing, which is if V and W are finite dimensional, remember what that means, right? Finite dimensional means that there are a finite number of vectors in any basis for that vector space. If there's a finite number of vectors in any basis for a vector space, no matter what basis you've chosen, that number is always the same. That number is called the dimension of the vector space, right? And so if there are finitely many such vectors, we call that finite dimensional vector spaces. If V and W are finite dimensional, it turns out there's not that many finite dimensional vector spaces. In fact, there's only one for each dimension. So if you are a 10-dimensional vector space, you're R10. That's what you are as a vector space. Maybe you were described as a polynomial space, like a space of polynomials or a space of certain continuous functions or something. Maybe you were described in some other way, but the point is what you really are is just a relabeling of R10. That's kind of how we thought about isomorphism. Saying that two vector spaces were isomorphic was saying that the only difference between the vector spaces is a labeling difference, essentially. So maybe you called the vectors F, G, and H over here, and you called them, V, W, and U over there. If V and W are finite dimensional, then V is some Rn, and W is some Rm, where N and M might be the same number, but they also might not be, right? So if the dimension of V is N, right, then it is isomorphic to Rn. If the dimension of W is M, it is isomorphic to Rm, and so on. So being a finite dimensional vector space means really you're just an Rn or Rm. And so when you're in the finite dimensional case, which in your linear algebra career is most of the time up till now, that means really, once we get the labeling under control, what you're really dealing with is this. And when you're dealing with this, there is always a matrix that represents T called the standard matrix. In this case, any linear map T has a matrix called its standard matrix such that T applied to the vector x is equal to AX, where A is this standard matrix. Okay, you can work out the size of A based on N and M here in the direction that T goes. Okay, now that's great because the idea, going back to what our goal was to make standard movements and projections manageable via matrix multiplication. Okay, and what we've done here is saying that, well, if we're dealing with finite dimensional vector spaces, any linear transformation between them is essentially just matrix multiplication. Okay, so then this means that if we can come up with a linear transformation T that does those things that we talked about, we are done, right? So if we can come up with T, a linear transformation that handles movements and projections we are done already. Okay. Well, that's nice. But there's a couple things we want to say here, right? So the first thing to say is like, why is this nice? Again, just wrapping up, right? Well, one, matrix multiplication is easy to do. All right, both by hand and computationally with the use of software, this is easy to do. Two, if we need to move or project multiple points, this is easy. How? Well, if I need to move or project multiple points instead of just one, which of course I'm very happy to do that, right? I'm very happy to move an entire like mesh grid of points instead of merely one point at a time. I can put those points as vectors in a matrix, right? Put points as column vectors in matrix and move them all at once. How does this work? If I apply T to the matrix whose column vectors are P1, P2 out to Pk, this is easily done by simply considering the matrix whose column vectors are exactly these things, right? I mean, that's how matrix multiplication works, right? Matrix multiplication works in this fashion, where multiplying a matrix with these as columns by another matrix is just this, right? Okay. And one more thing to say. If I wish to do multiple movements or projections. Now this is different than what I just said, right? Before I was talking about doing a single movement or a single projection of a list of points, right? So multiple points are being moved, but they're only being moved once. Multiple points are being projected, but they're only being projected once. This is different. What if I want to do multiple movements and projections? So I take, say, one point, and I want to move it, then project, or I want to move it and then move it again, and then move it again in some other way, right? Each of those movements being different. If I wish to do multiple movements or projections, this is also easy. Say A is movement 1, B is movement 2, and I'm doing movement 1, then movement 2. How would I do that? I have the vector to be moved, which is a point to be moved. I hit it with A, and then I hit that with B, so that this is represented reading from right to left as BAX. This is how matrix multiplication as a transformation works, right? So it's the first thing is applied here, and then I'm going from right to left, right? So the most recent movement occurs furthest to the left, right? So DCBAX is the movement that does the A movement, then the B movement, then the C movement, then the D movement last, right? Okay, so this is just basic, matrices as transformations thing here. Okay, and now recall some facts about a linear transformation. So recall facts about T. And if you like, I'll change this notation from T to F, keeping everything the same here, right? In this, I just said that any linear transformation between finite dimensional vector spaces, which we can just think of as Rn and Rm, has a matrix representative called the standard matrix like this. How do we find the standard matrix? Turns out there's really only one way that this goes. What is this A? What is this standard matrix? A. What I should say here is note, this needs to be linear to get this standard matrix. If it's not linear, there may not be a standard matrix, okay, that does what you want this to do. So what is this? The standard matrix A can actually be computed by exactly the columns are determined by what the map does to the standard basis vectors E1 to En. Right, where EI are the standard basis vectors which have zeros everywhere except a 1 in the ith slot. This is the ith slot. These are the standard basis vectors of Rn. Note that this is just I, j, and k if n is equal to 3. Right, so these are your standard basis vectors. All you have to do to figure out what this matrix is see what it does to the standard basis vectors. Okay. So then how do we get our matrix here? Right? There are some options. Okay. So options for getting A. The first option, if we know what the function is, we know it's linear, we can just construct it. If we have f, know it is linear, we can just find the matrix directly from seeing what it does to each of the standard basis vectors and then putting that in the matrix. That matrix will necessarily be this standard matrix. It has no other choice. And that's comes directly from the linearity, and this is the key. That has no other choice. I'm saying something about uniqueness here. Okay, and this is important for these remaining points too. Okay. Now, say we have a function and we don't know if it's linear. We could still find all of these, right? So say we have f. The question, is it linear? Well, here's the thing, right? You might say, what do you mean by you have f? Maybe you have a description in words of what f does, right? So maybe you know, because if I say you have f, you're going to say, well, that means I have the matrix, right? Well, no, right? You might have, your description of f might be, let f be the, transformation that rotates a given point, pi over 6 radians about the point P, and then translates it, this distance or in this direction by, this number of units, and so on, right? Like that could be your description of f, and then it's up to you to see whether or not that's linear, right? You might notice immediately that when I start asking you to translate things, that there's some tricky things going on in terms of linearity, and we'll get to that here in a second. But we have f, is it linear? So that's what we mean when I say we have f. Maybe we just have a description of what this thing does in words, okay? So then asking whether or not it's linear, remember this technically means checking that it satisfies the linearity properties, on every possible linear combination, right? On every possible thing that looks like this. Well, that's, we can't really do that. So then what do we actually do? We can still find each of these things. We could see what f does to each of these standard basis vectors. Then we could construct the matrix. In this same fashion. And then we could ask whether or not this matrix does what f does. Maybe I should say if multiplication by a does what f does. It has to do exactly what f does, obviously. It can't kind of sort of do what f does. It has to do the exact same thing. Okay. Here's the thing. Because of this bunch of words I said in the first part when I said that it has to be this thing, that's me saying uniqueness. By a uniqueness argument due to the linearity of this map, if this is in fact, if A, this thing that we have found, does what f does, then f has to be linear. And we have our A. Okay. Now, here's a question, right? So let's say we have f and we think it's not linear. Based on the context, maybe you have a good idea of some sample points or vectors that would make it clear that it's not linear. Okay, but maybe not. And so how would you do this? You would still construct this A. You construct the same matrix and check that it doesn't do what f does. Okay. So here, the point is that, again, if f was linear, or I should say f is going to be linear if and only if it matches what this matrix A does. If this matrix A that we've constructed doesn't match what f does, then f can't be linear. And if it does, then f is linear. You know, maybe you were wrong and f is in fact linear. And so, what if we have a function and we don't know if it's linear, right? The point is that the matrix multiplication that we construct with A has to actually do what F does. So we can't just make up a matrix, either in the same fashion and just say, yep, F is linear, like this does it, because that matrix is clearly not going to actually represent. It's not going to do what F does, so it's not. We can't use it, right? Um, so we need F to be linear for this to work. Now, right out of the gate, we actually have a problem. Okay, so right out of the gate, we have an issue. To see that, let's consider 2D translations. Okay, so let's move that point to that point. Let's move this point to this point by another translation, a different translation. Let's move this point to this point. The question, what do you notice? We'll call this translation like t sub 1, we'll call this one t sub 2, and we'll call this one t sub 3. Notice that these translations are by a vector, right? So when you describe a translation, you're saying, I want to translate this point by this vector. And of course, if you're applying the translation to the whole plane, what you're doing is shifting the whole plane by that amount. So when you talk about the translation as a map from, say, R2 to R2, right, this t sub I goes from R2 to R2. When you're talking about any of these transformations, you're saying that it takes any point in the plane and shifts it by that vector. So this point gets shifted there, this point will get shifted there, and so on. Every single point will get shifted by the same vector, and so on. Now, I asked you a question, which is, what do you notice? You might not immediately think about this because it might escape, what you recollect about Math 240. But the big problem here is these are not linear transformations. Even these super simple translations, they are not linear, period. Right? Well, why? Why is that right? Why are they not linear? You think in your head linear means like nice somehow. Or maybe you think geometrically that linear has something to do with lines. It does have something to do with lines, but you think to yourself, okay, translation is like moving along a line segment type thing. This seems like the most linear thing ever. But you might also remember that a linear transformation, especially between finite dimensional vector spaces like R2 and R2R, um, has to be represented by matrix multiplication. Matrix multiplication doesn't act like this. What do I mean? Recall, any linear transformation between vector spaces. I'm going to do it for vector spaces just to show you how deep this is. This is at the like fundamental layer. This has nothing to do even with matrices. This has everything to do with the actual linear transformations themselves, like the actual vector space structure itself. It doesn't have anything to do with even with R2, although it's easier to see. It's more immediate in that case. But any linear transformation here must send the 0 in V to the 0 vector in W. In fact, this was one of the ways in Math 240 that was, it's not exhaustive. You couldn't just do this, but this was one of the ways that you actually checked whether or not, it was like a quick check of whether or not a map was linear. Because if you suspected that a given transformation T was not linear, this was a quick thing you could check. It wasn't the only thing, right? Like you couldn't say, oh yes, it sends 0 to 0. It's definitely linear, right? There's plenty nonlinear maps that send 0 to 0. But the converse, right? If it doesn't send 0 to 0, it can't be linear. Let's prove that real quick. Okay. Well, T of the 0 vector, that's really T of a vector V minus another vector V. And if you don't like minus, we'll say plus minus 1 times vector V. It doesn't matter what the vector V is, right? This is true. If you take any vector in a vector space and add to it the scalar minus 1 times the same vector, you get the 0 vector, right? That's one of the definitions of the 0 vector. Okay, but by linearity, where's my, there it is. What is this? This is T of V plus minus 1 times T of V, which is T of V minus T of V, which is the 0 vector in W, which is what it has to be. So a linear transformation has to send 0 to 0, right? It has to send the 0 vector to the 0 vector. Here's the 0 vector. Does this transformation, does this translation send it to the 0 vector? No. It takes it to some non-zero thing. This translation would take it to some point up here, which is also not the 0 vector. In fact, any non-trivial translation, anything that moves the origin at all, is not going to be linear, right? So translations are a no-no. They are not linear. Okay. This actually causes, believe it or not, this is actually one cause for why we'll call it the Euclidean group, the group of Euclidean isometries in either the plane, space, or all that. It's why the mathematical description of them is a little nasty, like algebraically. Like if it weren't for this fact that the translations act like this, it would be much easier to describe what it is that's going on in terms of other what we'll call groups, mathematical groups. So we have to, there's a little bit of nastiness because of these translations. But then how do we deal with this? If not even a translation is linear, are we just doomed for all time? And the answer is no, right? So what is the solution to this? What is our fix for this? Our first idea, to see what's going on, go back to 1D. 1D is simpler than 2D in terms of the picture, so let's do 1D. Okay, so here's one-dimensional object. Here is my point X. And let's say that I want to move X 1 unit to the right, so that I want to move it to X plus 1. So I want to take the point X and I want to send it to X plus 1. That isn't linear, but let's try to represent it with matrix multiplication. So let us try to represent this with matrix multiplication. Now, you might say, well, I have this object in my one-dimensional space. It's a point. You could call it a scalar. In terms of a matrix, you could write it as a 1-by-1 matrix. There it is. But here I'm going to run into the same problems, even though this is a 1-by-1 matrix now. But what if, instead of writing it like this, we write it as a vector where we have just like fixed the other entry. And I'm going to fix the other entry in a certain way. Going to do it like this. Now you might say, wait a minute, why not do it like this? This seems even more natural. Well, because of this matrix multiplication that we're going to be doing, I don't want this second entry to be 0 because that's not going to lead to the product that I want. So I don't want that either. I want this. And the reason I want this will be made clear when I actually try to do this. So what I'm going to do here now is notice that this 2-by-2 matrix 1A 0 1 multiplying my vector x1, what does that do? This, in the top slot, this would be x plus a, right? And in the bottom slot, this would be 1. So that this matrix, if that's my transformation, takes my vector x1 and sends it to a similar vector x plus a 1. Is that essentially what I'm doing here? I've just basically relabeled what's happened. And the answer is, well, yeah, that's basically what has happened. What is this matrix? You might recall, again, depending on how in the weeds your Math 240 instructor got in terms of going over all the various types of, this is like chapter, if you're using the lay textbook, which I think UMD still uses the lay textbook for Math 240, this is all chapter 1 stuff. Maybe it's like, is it 1.7, 1.8? I can't remember. It's chapter 1 stuff. This is an example of what is called a shear transformation. And to see why it is called a shear transformation, look what it does to a generic point. If I do this matrix multiplication, what do I get? I get x plus ay and y, which does what? This is going to move if a is positive versus a is negative. This is going to move either to the right or to the left. This is going to move, to the right by a units, or to the right by minus a units, which is moving to the left. So like, look at how the lines y equals 1, y equals 2, say y equals minus 3, how these are moved. And the way that this goes, I'm going to draw these lines real quick. how this happens. So here's my xy plane. The line y equals 0 is fixed. How about the line y equals 1? So y equals 1 is to the right a units. I'll say to the right because of this arrow here. Y equals 2 is to the right 2a units. Y equals 3 is moved to the right 3a units, and so on. Y equals minus 1 is moved to the left a units. Y equals minus 2 is to the left 2a units, and so on. Okay. That's how it goes. So that is what this matrix is doing as a transformation. But for our purposes, we're just representing our one-dimensional point by this vector and then seeing that we can use this matrix multiplication to do what we want. And then essentially we get a thing that's back like this. Now we could move it back to our old labels, right? So for instance, let's just see like how this works with one-dimensional translation. So let's say translate translate x equals 7 by 3 units to the right. Now, obviously, you know how to do this in 1D, right? But writing this as matrix multiplication, rather than simply adding 3 to 7 here, translating by 3 units to the right would be done via this shear transformation matrix. The point x equals 7 in 1D is represented by this vector 7, 1. If we multiply this out, we get 10, 1, which corresponds to x equals 10. And so this does the transformation x equals 7 to 10. Okay. Again, you look at this and you say, well, I didn't need to do that in 1D to be able to do that shift. But the point is how this is going to translate, no pun intended, back into the two-dimensional case. So this is going to show us how this is going to work in 2D. And so, idea. In 2D, we represent our point xy with the following. So then we claim there is a linear f. Maybe I won't. I'll leave the. It doesn't matter. I could label these things, but I'm just going to say, claim there's a linear f such that f of the vector xy1 is equal to the vector x plus a, y plus b, 1. This would be a translation of the point xy by the vector, or according to the vector AB. Right? That's what this would be. Okay, so we are trying to represent a generic translation in R2 via matrix multiplication using the same trick that we did in the one-dimensional case. Okay. Now, if its standard matrix A exists, what we mean by that is if there exists a matrix that does the same thing here, right? That this is in fact linear, right? If this is in fact linear, there has to be a matrix called the standard matrix that does this, right? That f of vector is equal to the matrix A times the vector. If this thing exists, it must be what? A must be the matrix whose columns are how f behaves on the standard basis vectors, in this case I, j, and k since we're in R3. Okay. Again, this is our statement going back that this A is simply, its columns are exactly what f does on these standard basis vectors. Okay. So if this standard matrix exists, it has to be this thing. All right. Now, how do I find these? Right? Because looking at this, I'm upset. Well, maybe I'm not upset for the last one, but I'm upset that f takes in, I know what f does really only on vectors that look like this. So how do I figure out these two things? This one is easy. I can just plug in 0 and 0 for x and y, so I know how it behaves there. Okay, so that one's easy. This one I know. But these two I don't know directly because how does f handle a vector that has a 1 in its last slot? So I need to use linearity to find these. What do I mean by that? Well, what is f of 1, 0, 0? Well, I have to think of creative ways of using creative ways of rewriting one zero zero as these are not necessarily the same. These are not necessarily the same either. Okay. What do I mean? What am I talking about here, right? Notice from my definition of f, computing this is easy. F, I'm claiming, takes x, y1 to x plus a, y plus b, 1. So f of 1, 0, 1 is, let's just, here, I'll put this next to what it is I'm doing. F of 1, 0, 1 here is what? This is 1 plus a. 0 is b. And so this is 1 plus a, 0 plus b, which is just b, and then 1. And f of 0, 1, 1 is, again, putting this here so you can see, This is 0 plus a, so this is a, y plus b, so this is 1 plus b, 1. Now, this last thing, as I mentioned, is actually easy to compute. So I might as well go ahead and compute it here. F of 0, 0, 1 is simply, we look here, this is just a, b, 1. Okay. So now, the things I actually want to find are here. I've already found that. I need to find these two things. Well, f of 1, 0, 0 this is where my creative ways of rewriting these things come in. F of 1, 0, 0 is what in terms of these things? Well, it's really this vector minus that vector. So this is f of 1, 0, 1 minus 0, 0, 1. But linearity tells me that this is simply f of 1, 0, 1 minus f of 0, 0, 1. But I know what both of these are. So what is this? F of 1, 0, 1 we found was 1 plus a, b, 1. Minus f of 0, 0, 1 is a, b, 1. And so actually, this is 1, 0, 0. Okay. So that's f of 1, 0, 0. It is 1, 0, 0. Let's figure out the second column of my matrix. F of 0, 1, 0. Again, creative ways of rewriting here. This is f of 0, 1, 0, or sorry, 0, 1, 1 minus 0, 0, 1, which is, by linearity, f of 0, 1, 1 minus f of 0, 0, 1. Which is f of 0, 1, 1 is, what did we say that was? Going back on our previous page here, this is a, 1 plus b, and 1. Minus f of 0, 0, 1 from before is a, b, 1. Which gives us 0, 1, 0. So this f is going to send 1, 0, 0 to itself, 1, 0, 0. It's going to send 0, 1, 0 to itself, 0, 1, 0. And we know that it sends 0, 0, 1 to a, b, 1. And so our matrix A is the following. So the matrix itself, I'm not going to rewrite this step. Our matrix A has the columns f of 1, 0, 0, f of 0, 1, 0, and f of 0, 0, 1. These this is 1, 0, 0, this is 0, 1, 0, and this is AB1. So this is 1, 0, 0, 0, 1, 0, AB1. Right? Therefore, if f is linear, it has to be represented by this. The question is, does this work? So all we have to do to check that this actually works is that it satisfies, this is what f does, so this is what this matrix multiplication needs to do, right? So the question, what is A times the vector xy1? Okay, here's A. Here, if it helps to write xy1 next to it, right? xy1. This is x plus A, then y plus b, then 1. That's exactly what I claimed f did. So this is, if you were confused by this, I was writing out these list of 3 things earlier about like how we would treat this in terms of finding our linear transformation, or finding the matrix rather, that represents our linear transformation. Is we don't know if the f we seek is linear. We said, okay, we want an f that does this. If this is a linear transformation, its standard matrix has to look like this. We found what that standard matrix is, then we checked whether or not this worked. If this did not work, it means that no such linear transformation for the things we're doing exists. Okay, so that's the point. All right, but this one does. It works. And so in this way, we have fixed our translation, and now we know what this does, right? How to translate. We are going to call this translation matrix, this one here, we're going to call this translation by the vector AB. This is our 2-dimensional translation matrix here, and it will do our job. I'm going to do a quick example to show you how this works, and then we're gonna stop for today. So in fact, maybe I think I'll stop for today anyway. I've been going on long enough. Regardless, we'll pick up here tomorrow. So this will be where we pick up tomorrow. And yeah, I will see you all then. We'll mostly finish our discussion of computer graphics tomorrow. Maybe have to dip a little bit into Thursday for like 10 minutes to absolutely finish it, but we're pretty much done. And then we'll be on to portfolio optimization. And then basically rounding the corner on what's kind of like the last chunk of material for the course, and we've got, that I'll say is the core material. After that, we have some fun material that we'll have as an option that we'll get into that's not necessarily in the notes, but we're getting close to finishing out the notes. So you're going to get to see basically like a maximum amount of applications of this stuff, which is, fitting, right? That's the name of the course after all. But anyway, I will see you all tomorrow.